everybody. In the last lecture we started on systems chemistry and we were looking at the concept of how systems chemistry originated and the fact that combinatorial chemistry, dynamic combinatorial chemistry of the covalent kind as well as non-covalent kind plays a very important role in generating the array of constituent molecules or the library of constituent molecules which will get expressed by molecular recognition with a particular receptor, and then depending upon the right electronic and static fit, once we identify the key constituent, then the desired efficiency or the biological function can be optimized. And it is not necessary that this constituent library has to be available at the time of performing the supramolecular reaction with the lock, but it can be formed anytime by the dissociation or the reversible disconnection of the constituents to the components, and then the components can again combine in different ways to give you the desired constituent which will be the best fit for the lock. So that gives rise to the notion of the virtual dynamic combinatorial library of molecules, which actually are not strictly speaking virtual, but they become available as per the requirement of the receptor or the lock. Therefore, the desired activity can be achieved. Now, so we can now compare between the combinatorial library and the virtual combinatorial library. In this case, we have the molecular constituents. This is supramolecular constituents as well as molecular constituents. This is a collection of molecules. This is a collection of components, as I mentioned before. The association for the formation of the combinatorial library is the covalent bond formation, whereas for the virtual combinatorial library can be covalent association of the reversible kind or non-covalent association. This is non-reversible because once the final target or the final reactions, final set of reactions have happened and the final product has been formed, essentially it is non-reversible, but the virtual combinatorial library is of the reversible kind. So in this case, this is called neutral uninformed, but here it is the instruction which comes. So these are the instructed or the instruction, that is, so the instruction comes to self assemble internally or externally. The instruction can come for the species to undergo binding, and therefore this is more of an adaptive dynamic process. Whereas in the case of traditional covalent chemistry, once the molecules are formed, you can achieve a large degree of diversity in terms of the molecular skeleton and in terms of the architectural diversity, but by and large once they are formed, the final target is achieved. We work with these final targets only, whereas in the reversible association you can actually disengage either the covalent bond formation or the non-covalent bond processes in a reversible fashion, so that the components can again combine in different ways to give you the key constituents which function as a part of the virtual combinatorial library. And so this is adaptive dynamic process, whereas this is the corresponding systematic stepwise process using logical methods to achieve synthesis. And when we are doing the combinatorial chemistry to make the combinatorial library of molecules, actually we really do not worry about the target. Our idea is to make new exotic molecules which possibly will have different applications. So here this is in absence of the target, whereas here this is recognition directed. Okay, either it is self assembled or presence of target. So overall we call this chemistry as the dynamic generation of molecular and supramolecular diversity by target recognition directed self assembly. This is what was coined by Jean-Marie Le. So what is also important is that we now have the constituents, and the generation of the constituents is very important, and the process is, so the formation of the constituents depends upon the conversion process, where you combine the components to give a particular constituent. It depends upon the composition, and it depends upon finally the expression, which is the amplification process. So combination can give rise to different combinations, compositions. The conversion process is important, and finally once you have the library, what is the expression which leads to the amplification process. And all the different structural and interactional features, as I mentioned, all the different structural and interactional features which are necessary for the formation of this dynamic library of molecules, which we call as the virtual combinatorial library, will be present in the final molecules and the final set of combinations. Okay. So now we can look at some suitable examples. So to summarize, before we go into the example, we can say that the constituents of VCL results from a combination of its components by covalent assembly through a reversible chemical reaction, which we call as the molecular VCL, or by self assembly through reversible non-covalent binding interactions, which we call as the supramolecular VCL, and this is also referred to as the phenomenon of supramolecular polymorphism. Now this is interesting now, because polymorphism was with respect to the arrangement of molecules, and now the supramolecular association can be different for the supramolecular VCLs. So let us take the first example here, where we have created a virtual dynamic combinatorial library, a virtual dynamic combinatorial library of oligomeric helicates generated from a tritopic ligand, that is tris bipyridine, and metal ions of octahedral coordination. So, we can now draw it as follows. So, I have n such constituents plus n such m plus metal ions, and we can have they can have here, 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 plus n more. So, here we have the 5 metal ions, here we have the 6 metal ions, here we have the 4 metal ions, and it has been observed that these corresponding oligomers, all these are the constituents of the dynamic library and are potentially accessible by reversible interconversion. So, when you now put in a chloride ion, it has been observed that here, depending upon the cavity size, if you have a chloride ion, it templates the formation of this particular oligomer, whereas if you have a corresponding BFO minus or sulfate anion, then it will template this particular 6 metal structure. And so, depending upon the anions, different that is the requirement of the anions, once you add the sensing agent, then different kind of helicates will be formed. So, say you have a concentration of this particular structure, now it will reversibly dissociate to the corresponding metal ion and the corresponding tritopic ligand, and then this tritopic ligand will again self assemble to give very more thermodynamically stable entities, which will be the basis of coordination and stabilization of the chloride ion. So, this dynamic library can be created, and even the relevant molecule can be generated from this set of constituents by reversible dissociation and then association to give you the right molecule, which will be for the target metal ion, which will be sensed in the process. And so, in this case, this chloride or BFO minus, these are referred to as chaperones, which actually direct the self assembly process. This is also similar to the molecular chaperones, which are important in the folding of the protein molecules into the secondary, tertiary and the quaternary structure. So, the folding process is again directed by chaperones in protein self assembly as well. Now, we can take another example to demonstrate the importance of the virtual combinatorial library concept was devised to develop the process of recognition induced recognition by induced self assembly of the inhibitors of the enzyme carbonic anhydrase. So, the development of a suitable inhibitor of this particular enzyme was actually taken up by the concept of this VCL, and in this regard different components were selected. The components contain the aldehyde and amino functionality. Okay, and these aldehyde and amine functionality can now form the imine bond, and therefore the product thus contains the imine bond, and the particular imine whose structure resembles that of the inhibitor of the enzyme carbonic anhydrase was actually characterized by this process. And if the match is not good, then again this imine bond can again undergo reversible dissociation into the corresponding aldehyde and amino, and now these aldehydes and amino can again combine in different ways to form another set of molecules of which are a part of the library, and then we will be able to direct the population towards that particular molecule which is very specific to the inhibition of the enzyme which is the carbonic anhydrase. So, we are actually here sampling a set of molecules, making new imine molecules, checking it for the target binding with the inhibitory activity of the enzyme carbonic anhydrase. If it does not inhibit, then we actually look for another library. That library can be accessed depending on its availability. That is, once we give it the instruction to be produced, then again the reversible dissociation happens. Again the components react with each other, give a new set of library molecules, and we can screen it for a design of the right inhibitor. So, by this process of screening, what will happen is that the purpose is to shift the equilibrium population towards the imine product that has the structure closest which is closest to the known strong inhibitor for that enzyme. So, let us consider I would like to take a different color here just to emphasize the different reactants. Then we have got a set of amines A, B, C and D. These are the components, and from the aldehyde side we have this aldehyde, we have this aldehyde, and we have this particular aldehyde. So, these are all the components and we can have reactions between these amines. We can have reaction between the amines and the aldehyde to give the imine bond formation. So, a possibility exists of 12 products, 4 into 3. For example, we can get the reaction with this and this can give us this particular product, or we can get the reaction of this with this can give us this particular product. And we can also have another reaction of say this with the corresponding this. So, this can give us plus and this was found to be almost equivalent to the actual compound, which is a strong inhibitor. So, you can see that this compound is structurally quite similar to the compound which actually inhibits the activity of carbonic anhydrase. And also to tell you that this is an enzyme which is used for the conversion of carbon dioxide to bicarbonate plus proton, and this is a zinc containing enzyme. So, in this way you are able to actually create the components, you are able to create the dynamic library, and then the dynamic library can be screened, and in this way you will be able to get to the required target molecule which models that of the actual compound, and therefore we can now produce sufficient concentration of this particular targeted compound. The equilibrium can be shifted in such a way so as to form more of this compound, first by reversible dissociation and then combination to form the desired compound, which competes with the well known compound which is a strong inhibitor for carbonic anhydrase. And then this process of dynamic combinatorial library is very important, because is a very powerful concept, because when you have got a set of molecules which can combine with different ways, instead of wanting them to react in all possible ways and give you large amount of products, it is better if the molecules themselves decide with whom they want to assemble. So, the process of self assembly should be more like a self organized process. So, self organization becomes a key player here, rather than pushing the equilibrium or pushing the reaction condition towards forming all possible products such that none of the products can be obtained in abundant yield or will actually be having a particular useful application. So, the idea is that when you have this combination of molecules, the idea is that they self organize, or we know that we have heard of self sorting mechanism. They sort out between themselves how they will self assemble with each other, and the resulting product must have an interesting application. Then the utility of this combinatorial approach of a library of molecules becomes extremely useful, and we can demonstrate this very useful application of such a self assembly process, which is mediated by non-covalent hydrogen bonds in the design of a gel via the concept of dynamic combinatorial library or chemistry. So, let us take an example, the first molecule. we call this A. Then we have the molecule B. Then we have molecule, I am calling this D, and the molecule C here. So we have the amine functionality here, we have the amine functionality here, we have the aldehyde functionality here, and we have the aldehyde functionality here. So we can have now different combinations of aldehyde and amine to give you the different products. 4 possible products can happen. So 4 different products can be formed. So these are the components of the DCL, and so what now the system does is a process of self sorting or self organization. Self sorting or self organization command is what is most important, and it leads to the formation of a supramolecular gel by the combination of A plus B. And so the selection is done in the way that the selection of the molecules or the selection of these components to combine to give you the gel is done in such a way that it forms the most stable supramolecular assembly and the one which is also survives in this race of combination. So in this way the formation of the most stable and organized self assembly process is a reflection of prebiotic Darwinism, which is driven by self organization. Okay. So the process is the prebiotic Darwinism, which is driven by self organization and which tells you that that particular entity will survive, which is the fittest constituent. So the concept of fittest constituent becomes relevant, and in this regard this particular gel which is formed is the most stable entity. Now let us look at the structure of this gel. I would like to draw it. So this gel I have the NH here, so H here, H here, and there is now a hydrogen bonding. Now here also there is a hydrogen bonding. Then here you will have here so this double bond will be here. So now we have got this hydrogen bonding NH, NH, this is N, and so this will now come from N. Okay. So this is the gel, the tetrameric gel which is created, but what is more important is here you have the ribose, and then here you have the ribose, here you have the ribose, here you have the ribose, and then further this particular amino has reacted with this particular aldehyde to form N H and double bond R. So this is present here, and the R group is this particular part. This is the R group here. So this is present here, this is also present here, this is present here, and this is also present here. So first it forms the covalent association happens between A and B, and then there is a supramolecular association which creates this very stable gel structure. Stable. It creates this stable gel structure. So this is the key constituent, the fittest constituent, because it involves both irreversible association and then supramolecular reorganization, self-assembly to create a very stable gel-like structure. And initially we have mixed this in 1:1:1:1 ratio, 15 millimolar each, and in sodium acetate buffer. So under these conditions we saw that this particular gel formed favorably. We can also have the other combinations. So this was C. So we can have A plus C to give you F. We can have D plus C, this and this, to give you G. We can have D plus B to give you H. So we can have these four products, and what is formed is E is 39%, F is 8%, G is 42%, and H is 11%. So the combination of D plus C also is quite abundant, it is 42%, but none of these F, G, H form gel, it is only E that forms the gel-like structure. Therefore, in this regard I would say that that E and G are actually favoring the formation of more stable entities, therefore they are agonist, but F and H are antagonist in this overall library of molecules. So this association leading to formation of E and G is favorable compared to that of F and H. So this is nicely depicting the overall concept of gel formation in an applications of DCL. So with this I think I hope I have been able to impress upon you with these examples which we have discussed, the relevance of dynamic combinatorial library, virtual combinatorial library, and how these concepts can now be further utilized for understanding interesting biological processes, and we can combine this chemistry to understand origin of formation of molecules, which eventually became a part of the development of molecules which constitute life. So thank you very much. With this I think we come to a completion of all the lectures of this course. Thank you.